So I have to finish up section 1.3, but before I do, I want to review some of the concepts that we got to. So we talked about, at the end last time, this indeterminate form 0 over 0. Right, so when you plug your x value into your limit and you get 0 over 0, that's called an indeterminate form because we don't really know what the limit is still. I wanted to give you a couple of sort of review problems here that deal with this form. For example, if I give you something like the limit as x goes to 5 of 5 minus x over x squared minus 25, how would you deal with that? All right, so first of all, if you plug in 5, you see that you get this indeterminate form, right? If you plug in 5, the top becomes 0. And if you plug in 5, 5 squared is 25, the bottom also becomes 0. So one of our tricks, one of our methods to help simplify this is to factor. So one thing you can do with 0 over 0 is factor. This will become the limit as x goes to 5 of 5 minus x over, this guy's a difference of squares, so x plus 5, x minus 5. You haven't really done anything yet because you still get 0 if you plug in 5. So you have to find how to reduce this. How does this reduce?
Put a negative on the top.
Yeah.
And make it
So these factors are opposite signs. And 5 minus x and x minus 5 have opposite signs, so what's going to happen is they're going to reduce to negative 1. So this will become the limit as x goes to 5 of negative 1 over x plus 5. Now I don't have 0 over 0. I don't have a problem. If you plug in 5, you get negative 1 over 10. Done. So this is one technique we learned to help deal with this 0 over 0 case. This is the factor and simplify situation. Questions about that one or not? That's okay. One? Alright. So let me make it a little higher. The limit, so example, let's calculate the limit as x goes to 0 of 2 plus x under the square root minus root 2 over x.
Rationalize.
Right. So this guy is another 0 over 0 form. Right? Because if you put x equals 0, you get root 2 minus root 2. And if you put x equals 0 in the bottom, you get 0. So this is the same problem. But we're not going to factor and simplify in this case because it doesn't really factor. So instead, we're going to use our rationalize trick. So I'm going to, let me come down with that. I'm going to take the limit as x goes to 0 of root 2 plus x minus root 2 over x. And what am I going to multiply by? The conjugate. So I'm going to multiply by the conjugate of the top because I'm hoping if I get rid of these roots, something will cancel. So the conjugate of the top is root 2 plus x plus root 2. That's what I at the top and bottom. Now this whole binomial here has to get multiplied by this whole binomial. So you have to distribute this guy to both of those, distribute this guy to both of those.
Isn't it just that one square minus that one?
It is, but why?
Because it's special formula.
But how do you prove the special formula? You distribute.
Oh, yeah.
So,
Same time.
if you remember the special formula, you're more than welcome to use it. This is the difference of squares squared. Okay? If you don't remember the special formula, then you have to distribute it out and figure out what happens. So, what's going to happen, if you did distribute it, the root 2 plus x and the root 2 plus x would end up giving you just 2 plus x. All right, that makes sense? This root 2 and this root 2 would end up giving you minus 2. What happens when you crisscross here? They cancel, right? Because one of them is going to be negative and one of them is going to be positive. So the middle terms, the O and the I of the FOIL, cancel out. On the bottom, should I distribute this x? No. Your hope is that the x actually cancels because that's what's causing you problems in the bottom. So you leave this factored. And don't forget your limit because we still haven't evaluated the limit. It's bad. It's bad math on my part.
And then the x's cancel.
Right, exactly. Luckily, the top simplifies beautifully. 2 minus 2 leaves you with x on top. You also have an x factor on bottom. The x factors go away, right? They reduce to 1. So you're just left with the limit as x goes to 0. 1 over 2 plus x. Now there's no problem plugging it in because if you try to plug it in, you don't get it in determinate form. You don't get 0 over 0. Instead, you get
1 over 2 square root 2.
1 over root 2 plus root 2, which is 1 over 2 root 2. Which you could rationalize, I guess. If I care that much. If you had to rationalize this, like if you're trying to match a specific answer in the back of the book or something, you would multiply by root 2 over root 2. So it would become root 2 over. On the bottom, root 2 times root 2 is 2. So root 2. So if it's on multiple choice, you'll see either this answer or this answer. If it's on short answer, I don't care which one you do. So that was our second sort of skill, right? Rationalize. Bueno? So this one doesn't quite fit any format that I gave you, but still can come up. So let's talk about it. Limit as x goes to 0 of 1 over x plus 4 minus 1/4 over x. So what happens with this guy? What's the problem when you plug in 0? 0 over 0 again, right? Because on top it'll be 1/4 minus 1/4, which is 0. On bottom it'll be 0. What do you think we do with this? Factoring doesn't make much sense. There's not really anything to factor. Rationalizing doesn't make much sense. There's no roots. I would get a common denominator and try to simplify it that way. Right? Somehow you have to simplify this so that this x in the denominator goes away. So one thing you could do is get a common denominator on the top here and see if anything goes away. Right, so if I want a common denominator, I need a 4 over here, and I need an x plus 4 over here. So I would put 4 over 4, and then I would put x plus 4 over x plus 4. This will become the limit as x goes to 0 of 4 over 4 times x plus 4 minus x plus 4 over 4 times x plus 4 all over x. So all I did was multiply straight across here. In the bottom I didn't bother multiplying because hopefully something's going to cancel. Now you actually have to combine these. Be careful when you combine this, negative gets distributed, right? So this will actually end up being the limit as x goes to 0. When you combine these two fractions, you'll get a negative x, but the 4's will cancel, right? Because it's 4 minus 4. So this top part, all that's left is this negative x. Yeah, 0 over, if you plug in now, you might want to try to plug in. This will be 0 on top, and this will be 0 on bottom still. So this is really the guy we need to get rid of. So what can we do? Flip it up, right? Multiply by the reciprocal. Think of this as x over 1. Then it gets flipped up and you multiply by 1 over x. So this is the same thing if I take the limit as x goes to 0 of negative x over 4 times x plus 4 times 1 over x. And now I'm getting somewhere. Now these x's cancel. One's on top, one's on bottom.
Over 16.
Now there's no problem plugging in 0. If I plug in 0, I'll get 1 over.
Negative.
Oh, I dropped my negative. It was just too heavy for me to carry. Getting old. I can't carry those negatives anymore. You guys are young still, so it shouldn't be a problem for you. Yeah. So negative 160. So even though this wasn't specifically one of the skills I mentioned, like factoring or rationalizing the denominator, this is another trick you might have to use. But if you have fractions from the top, you can combine them and then hope, pray, something cancels. Okay. So the last sort of two things in section 1.3. There's something called the squeeze theorem that you can use to evaluate limits. So this is 1.3. This is the new stuff. Stuff I didn't get. Squeeze theorem. It comes up. It's mildly interesting. There are more interesting things in the world, I guess, but you'll see it mentioned a bunch of times, so let me tell you what it is. If you have some function trapped between two other functions, for all x values nearby some c, then in some way I've surrounded my y values, my function values, by two other functions. What happens then is you can take the limit of all of these. Right? So if this is true, then the limit as x goes to c has to obey the same inequality. So this is actually not quite the squeeze theorem. This is pre-game. This is just true. Since h is less than f, then the limit of h will be less than the limit of f, etc. The squeeze theorem goes a little bit further. So additionally, and this limit are the same, what do you think happens?
We squeeze the limit of x in there.
Right, so if these outside limit, if the limit that's supposed to be bigger than f and the limit that's supposed to be less than f are the same, then f must be the same as them as well. Right, like if this is 1 and this is 1, then this has to be 1. Because there's no more room for it to be anything else. So if these limits are the same, then they're all the same. So the limit of h of x is equal to the limit of f of x is equal to the limit of q of x. Let me give you an example. This is your buddy. This is your pal. You guys like this guy. Find the limit as x goes to 0 of absolute value x times cosine of 1 over x. First of all, plugging in 0, we just found out, well, maybe this isn't quite what we did, but it's very similar. Plugging in 0 here is going to give us trouble. This is one of those oscillating bad points. Right? Cosine of 1 over x, sine of 1 over x, they oscillate so madly around 0 that you can't find a limit. Okay? But this is not just cos 1 over x, it's cos 1 over x times something. So we have a chance because this multiplication might help our limit exist. What happens here, if you want to actually find this limit using the squeeze theorem, you have to bound cos 1 over x. So can you give me two numbers that are less than, one number that's less than cos 1 over x and one number that's greater than cos 1 over x?
2 over x and 1 over 2x. Cos. No. Okay.
I have no idea if that's true or not. It's more simply, what's the highest cosine can ever be? 1. What's the lowest? So certainly this function, whatever you put inside of it, because it's a cosine function, this guy's going to be between -1 and 1. But I don't actually care about this function. I care about absolute value of x times this function. So I'm going to take this inequality and multiply everything by absolute value of x. So I'm just going to do times absolute value of x times absolute value of x times absolute value of x. Does that change my inequality?
No.
This, I actually purposely picked absolute value of x to make this a little simpler. Because if you multiply by a positive, it's never going to change your inequality. And I know absolute value of x is always positive. But how does that help me? Well, on this side, I have negative absolute value of x. On this side, I have the function, in the middle, I have the function I care about. And on the other side, I have positive absolute value of x. So I'm in one of these situations here. So I can take the limit of everything and see what happens. Because I'm concerned with the limit as x goes to 0, I'm going to drop one of these in there. Limit as x goes to 0, suck that down. Limit as x goes to 0, how do you like that? Limit as x goes to 0. Boom. And so in the middle, I have no idea what that is yet. But on the outside, I know the limit as x goes to 0 of absolute value x, that's a v. What happens as x goes to 0?
0.
It's actually a downward v, right, because it's negative. But it doesn't matter, you can just plug in 0. If there's no 0 over 0 indeterminate form, there's no problem. If you plug in 0, you get 0. This guy I don't know. Same thing here, if you plug in 0, you get 0. So we squeezed the limit we care about between 0 and 0. So that means that this inside limit has to be equal. we know if it were just cos 1 over x, we'd have a problem, right? This guy's got some crazy oscillations in it. Okay, just like sine. But if we multiply that by absolute value, hopefully you recognize absolute value. Oh, you do. See what it does? It dampens it.
That's creepy.
So the absolute value multiplication is make this guy's going to 0, so it's taking him along with it.
Zoom out.
Yeah.
So it's following like the V as an asymptote?
Well, kinda. It's getting, you're talking about as x goes to positive and negative infinity.
Yeah.
It still has a cosine. It's still going to have zeros every now and then. So it's just going to grow and then start getting smaller.
But like the outsides of it.
But these maxes here, these guys are going to be following an absolute value. That's correct. All right. Okay. So the squeeze theorem is mildly useful every now and then. It's not the end of the world. Don't understand it. It's helpful with trig functions because as soon as you have a trig function, you can bound between -1 and 1. And then you can multiply and divide by things and try and work with them. So I told you there's one other thing I have to talk about in this section. I told you that one of the indeterminate, or one time that you get 0 over 0 is when you have what I call a special trig limit. So there's two special trig limits. One of them is the limit as theta goes to 0 of sine theta over theta. This is equal to 1. So this is just kind of like in a blue box, and whenever anything's in a blue box, then you know you have to memorize it, and know it, and understand it. And the other one has to do with cosine. The limit as theta goes to 0 of 1 minus cos theta over theta. Oh, 0. Yep. Now, your book goes through this proof, and it's nice. I don't want to do it. Because it requires geometry in the area of the sector of a circle, and it is a bit. But I will give you something kind of cool. Okay. So I'm gonna show you really quickly why this is true, or one quick way you can sort of believe that this one is true. We don't care about this one. So if you look at this guy here, I graphed 3 things for you. I don't know if you kind of see that. And I'll throw a graph up here for you too. So the question that I'll answer really quickly: why might something like this be true? And kind of the logic, skipping the geometry part and using these graphs instead, is that you can take the function y equals x. So this guy, instead of theta, think of him as y equals x. Because that's what I have to graph up there. And this guy, think of him as y equals sine x. If you graph y equals x, what does it look like? Diagonal line, right? 45-degree angle. Slope 1. Right, so on my graph there, that's red. The red guy is y equals x. Or just theta. If you graph sine x, it actually ends up looking, he's the blue graph. It ends up looking if you graph tangent x, which is the green one, it ends up looking something like. So if you had to guess at an inequality between these three things, focusing on the first quadrant here, so for x's that are positive, what would your inequality be between those three functions? Which one's biggest, does it look like? Tangent. And which one's smallest? Sine. And this is true. I mean, I know the graph gets very, if you even look at the graphing calculator here, these guys get so close to one another, after a while they're the same thing, according to the graphing calculator, because it's rounded. But you can use some geometry and prove that this is true. My question is, how does this help me get at sine theta over theta or sine x over x? And again, I'm kind of just worrying about x greater than 0. So what I can do to get this sine next to this x is I can take this inequality that I've accepted as true and divide everything by sine. What's sine over sine? 1. Okay. X over sine x. I'm just going to leave him alone for now. What about tangent over sine x? 1 over cosine x, or secant x, right? How'd you get that? Yeah, tangent sine over cosine. So if you take sine x over cos x and you divide out the sine, you flip it up and the signs cancel. So you get 1 over cosine, or secant. Guess what I can do now? Squeeze. Squeeze. Squeeze, 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 squeeze. Boom. Right, take the limit as x goes to 0 of these bad boys. What's the limit as x goes to 0 of the constant 1?
1.
1. This is always 1. I don't care what you make x go to. You're always getting 1 out of this. This guy I'm going to leave alone. It's too messy for me. What about the limit as x goes to 0 of 1 over cos x? 1 again. Why?
Because just the humps flipped over.
Yeah, so, yeah, you can think of the secant graph. It has a minimum right here. It's the bottom of the hump. Or you can just plug in 0 to cosine. Right? Cosine of 0 is 1. 1 over 1 is 1. So what does this limit have?
1.
Why do I care about this limit? Because it's the reciprocal of this limit. So if this guy goes to 1, then I can flip him, and I can ask, what's this? This guy's got to be 1 as well, because if you plug in x to this, you get 1, according to this guy. And then when you flip and multiply, you get back here. So, if you believe that tangent is greater than x's, which is greater than sine, then you know this is true. If you don't believe it, then you can read the proof in the book with sectors and circles and ask me if you want clarification. I went through this because it's another example of squeeze theorem. Now, I actually want to be able to use these special limits in homework exercises. So let me give you some examples of how you might be using these. So So I could ask you, for example, find each limit. A. What's the limit as theta goes to 0 of sine squared theta over theta?
It'll equal sine theta, which is sine 0.
Yeah, so what the whole trick is with these guys that have trig functions that sort of resemble these special limits, you have to figure out how to break this apart so that it has one of these in it. The other thing you really want to pay attention to is that you're going to 0. Because these limits are only true if you're going to 0. If you're going to pi over 2 or pi or anything else, these don't matter. But we are going to 0. And I can break this up to look like this. I can make this the limit as theta goes to 0 of sine theta over theta times what would be left? An extra sine theta. Knowing that I want to get one of these in my problem, I split the sine squared into sine times sine. But then we have a property of limits that says if you have a product, you can take the limit of each of the factors. Right? That was one of the properties we went over last time. Limits work well, behave nicely with basic operations. So this guy I know by my theorem or my formula over here is 1. This guy I know by direct substitution
0.
is 0. Right? Because if you plug 0 in here, it'll be sine of 0. Sine of 0 is. So altogether, my limit equals 1 times 0. Well, okay, that's 0. So when you're dealing with a sine theta and a theta, or a cosine theta and a theta, and you're going to 0, you want to make your limit look like one of these first, and then deal with the leftover later. Let me give you. The limit as x goes to 0 of 1 minus cos 3x over x. You got to be careful with this one. Right? You want to look at this, right? You want to say it looks pretty similar to this, so it's probably 0. Which maybe it will be, but it's not exactly the same as this. So what you need to do is a little bit of manipulation to make it exactly the same as that. More specifically, these need to match. If this is 3x in here, this has to be 3x down here. And then you're in business. So in order to make these match,
Multiply times 1 over 3.
multiply this guy by 3, but then you got to do it to the top as well.
And then 0.
So now, actually what I'm going to do, I'm going to leave all of this inside the limit. But this guy's a constant, and one of our limit rules says that multiplication by a constant can come out front. Now this is okay, yeah, go ahead.
Does it matter that we still have x approach 0?
Kind of, yeah. Yeah, we need to take care of that, right? Because this doesn't match exactly, right? Because this has theta, theta, theta. So you would want, 3x, 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 or x, 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 or theta, 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 or whatever. Okay. But whether x goes, let's put it this way, if x goes to 0, what does 3x go to?
Still 0.
It goes to 0 as well. So you can think whether you calculate this using x goes to 0 or 3x goes to 0, they're equivalent. Okay, so these all actually do match. So as long as it's a constant multiple, it doesn't really matter. But if it's like an addition, well, let's not get that complicated. So this whole limit here is equal to what?
0.
0. That's what I didn't prove it, right? But that's what this says. Except instead of theta, we have 3x, 3x, 3x. That's okay. So our limit will be 3 times 0. Lest you think that every limit is 0 that has a trig function in it. I'll give you one more example. The limit is x goes to 0. Sine 7 theta over theta. Oh, x,
theta.
sorry. I'm using x. So you're seeing this trig function in this x, and you're thinking you want to use one of these. But in order to even start using one of these, first you want to make sure you're going to the right thing, but since we're going to 0, that's not a big deal. But second, you need to make sure these match. So how are we going to make them match?
Multiply.
7 on top and bottom, right? So you can put in a 7 here and a 7 here. Now what I'm going to do is pull out the bottom 7 because he doesn't fit my format. So the bottom 7 is going to be yanked out as a
1 over 7.
1/7. But you got to keep them on the bottom. Now this guy, whether x is going to 0 or 7x is going to 0, it's the same thing. So this limit right here is equal to this guy right here is equal to what? 1. Why?
This is the opposite.
It's the reciprocal of this. Right? If this limit's equal to 1, then you know automatically that the limit of the reciprocal is also equal to 1. Because if you flip this, you get the reciprocal of 1, which is